In this section, we will look at another type of neural network called convolutional neural network that we generally use for images. So what exactly is a convolutional neural network? So convolutional neural network is one in which we have at least one layer that does a convolution operation. So that takes me to the next question, that what exactly is a convolution operation? So if you see the dictionary meaning of convolution, it means combination. So there is a combination of the image data with some filter or kernel to actually extract some features of the image. But the main question is, while we have the artificial neural networks, why do we need a convolutional neural network? So it turns out that, say, for a simple neural network, if you have an image of a large dimension, then the number of parameters becomes so large that it is not feasible to train a neural network. So let's take an example of an image with the dimensions 1024 cross 1024. So if you have like 10 neurons in the first hidden layer, the number of features will be around 3.1 million, and if you multiply it by 10, you will get 31 million parameters in the first hidden layer, which is not feasible even for a modern day computer to actually calculate very fastly. Hence, we need a convolution operation. But what exactly is a convolution operation? So it turns out that the convolution operation works on the principles of filters. So the lower layers in the neural network detect edges and the low-level features, and as we go deeper into the neural network, that is, as we go from left to right in neural network, it detects high-level features. So we can simulate this functioning of neural network by using filters. So we can detect the low-level features and the high-level features by using filters. So with the help of filters, we can drastically reduce the parameters of the model from 31 million to 9, 6 or 25 depending on the size of the filter in each layer. So mathematically, how does this operation happens? So suppose that you have a filter of size 2 by 2 with the following values like W, X, Y and Z, and our image has the following values A, B, C, D, E, F, G, H, I, J, K, L. So if you want to slide this filter across the image, this is the way how you'll do it. The first cell of the output is the dot product of the kernel and the sum portion of the image. AW plus BX plus EY plus ZF is the first output cell in our output image. Similarly, for other cells, we do the dot product by sliding our window on the image by 1 to the right, and when the right is done, we slide 1 to the down. And we do this until we slide all to right and all to down. So this is the convolution operation mathematically. If you want to visualize that how exactly the convolution operation happens for an image, as an image is a 3-channel image consisting of RGB color space, then this diagram will help you in understanding that. In order to actually apply a filter on a 3-dimensional image, by 3-dimensional I mean that our image has a width, height and channel, so we need filters which exactly are 3-dimensional. So our filter also have a width, height and a channel. So for 3-channel image, we need a 3-channel filter. So this is convolution operation over volumes. As you can see that the individual channel of the filter is multiplied with the individual channel of the image, and then finally everything is added to get a final output. So that was about the convolution operation. As the name suggests, if there is one layer that is containing a convolution operation, then we have a convolutional neural network. We will see in a short while how to do a convolution operation in TensorFlow 2.0. But before that, just a little bit, 2 more concepts before we go to that. Then we have something called padding. So what exactly is padding? So when we do multiple convolution, the size of the image decreases. In case we do not want the size of the image to decrease, we add an extra padding of zeros around the image. So in this case, the output size will be the same as the input size. So the general rule to calculate the output size is n minus f plus 1. where n is the dimension of the image, f is the filter size. In case we have a padding, we have n plus 2p minus f plus 1. Another concept is of stride. As I told you that we slide the window on the image first to the right, then to the bottom until we have covered all the cells. But we can actually customize this sliding behavior. We can say that do not slide the window every time by 1, but instead slide it by 2. So it will shift 2 cells to the right in every convolution operation and 2 cells to the down in every convolution operation. So the formula for calculating output size with stride is n plus 2p minus f divided by s plus 1. Just a little bit of general guidelines while actually working with convolutional neural networks. So in a convolutional neural network, an input is generally an image, first of all. So we perform convolutions to learn features from image. Traditional tabular data, we consider columns as the features and the labels as one column, right? But in a convolutional neural network where an input is an image, we do a convolution operation to learn features from images. We do different type of convolutions to learn different features. So these convolutions are stacked in form of different layers called convolutional layers. Generally, as we go from left to right, the size of the input image keeps on decreasing. So the size of the image keeps on decreasing and the number of filters keep on increasing. So it's a general rule of thumb. Whenever going from left to right in a convolutional neural network, the size of the image decreases and the number of filters increases. So as it is very evident from this diagram, we have an input that is an image of a robot. We do convolutions to learn some features out of the image, and we do multiple convolutions as these are convolutional layers, and then subsampling is another form of saying stride. That is, we actually reduce the size of our output image so that it becomes manageable to actually flatten it and then perform a classification or regression task. So after subsampling, after a lot of convolution layers, as I said that from going from left to right, the size of the image keeps on decreasing. We have one layer where actually we flatten output from the convolutions, and then we have a fully connected layer, the one that we saw in the previous section, that is a dense layer, in which we have a neural network that is fully connected to each other. And then finally, we have an output layer where we apply an activation function like softmax or sigmoid to get the required output. Well, that's it for the convolutional neural network part.